Section 3.3 is called Orthogonality, but it's mostly a section about lines and planes in space, and the concept of orthogonality, which means things being perpendicular, is used. So in this course, when you read the word orthogonal, perpendicular, that means things are at a right angle. Okay. So we start with by defining lines in R2, and we're going to extend that concept afterwards to lines in R3 and so on, and even lines in Rn that we can't picture, but that still exist. So there are two ways to view a line and to define it, and we're going to use the concept first of orthogonality to define a line. So imagine I have a line in space like this. Okay, how could I specify mathematical objects that would how could I characterize this line using mathematical object that would specify completely this line and would make it unique? Okay, there are different ways. You could say maybe the most intuitive way of defining a line is if I have 2 points on that line, I can define what that line is. That's one way. Another way would be, if we've got the same line, if I've got 1 point, but I know the direction in which this line is going, I could specify that line. Okay, so given that vector, which is illustrated by the arrow and a point, there's a unique line that I can draw that goes through the point and that points in this direction. And same goes for the 2 points. If I've got 2 given points in space, in R2, or even in space, there's a unique line passing through these 2 points. But and we're going to return to those. We actually sort of considered this case already in section 3.1, and up to a certain point, almost this one as well. We're going to return to them. But the way we're going to define a line at the beginning of section 3.3 is the following. Same line here. If I have a point and a vector that's perpendicular to the line, there's a unique line perpendicular to that vector that's passing through this point. And that's the view we're going to adopt right now. So imagine we're going to call this, this is the word I was looking for. We're just going to call this vector n. N is for, it's going to be called a normal vector. Okay. Normal is a synonym for perpendicular. You could say it's a perpendicular vector. You could also use the word orthogonal vector. So all these 3 words in this course mean the same thing. Normal, perpendicular, orthogonal. Okay, so when you see one of them, you have to think about things that make a right angle. Okay, so we're going to call that vector n. We could also, since we're in R2, it's a vector, let's say it has coordinates AB. Now, remember, right, the origin could be here, somewhere else, okay? If I say that n has coordinates AB, it means that if AB is a point in the plane, okay, n would be a vector starting at 0 and at the origin ending at AB. But if I translate that vector in space, I could put it here. So when I say n is equal to AB, remember that means it's associated to a point AB, which is such that the vector connecting the origin to that point forms the vector n. Okay, but this guy here, that I could call it P naught or P0. Okay, I often say P0, but some people say P naught. That's a point through which the line passes through, and I could say that it has coordinates x0, y0, or I could also say x naught, y naught. Okay, and that's a real point in space. Okay, it's not a vector. But AB is a vector that's perpendicular to the line that passes through P0. Okay, so now I've got P0, I've got N that completely specifies my line. There's a unique line going through this point, P0, that's perpendicular to vector N. Okay, so let's write this up. Here we have it. A line in R2 can be defined by a point P0 on the line and a vector N perpendicular to the line. Okay, it's important that we're in R2. If try to extend this definition to R3, we'll see that we'll have, well, there's a little surprise coming up. So we'll stick to R2 for now. Okay, now what I want to characterize is any point P that's, okay, that's on the line, an arbitrary point P with, let's say, coordinates x, y. Okay, now take a look at this. If I look at the vector going from P0 to P, that vector is going to be perpendicular to vector N. Okay, so that's a sentence I can translate into a mathematical equation. So I can write, if P is any point on the line, then it means that the vector going from P0 to P is perpendicular to vector N. Now, whenever we say that things are perpendicular, we've got the right tool now to translate this statement. That tool is the dot product. When two vectors are perpendicular, their dot product is equal to 0. So this means P0P dot product N is equal to 0. Notice how I write my my course notes is exactly how you should write down your assignments, right? So notice that I'm always putting equations within sentences and starting them with a capital letter, finishing them with a period, and so on. Okay, so therefore, now I'm at a point where I can write down what the coordinates of the vector P0P are. So remember, that's that vector P0P that's in green here in the picture. Well, they're both in green. Maybe I should put another one, the other one in a different color. Let's say I put N in red. Okay, so P0P is in green. I get that vector by subtracting the coordinates of P0 to the coordinates of P. So coordinates of P are x and y, and the coordinates of P0 are x0 and y0. So I need to subtract them together, and I take the dot product with N, which has coordinates AB, and that dot product is 0. So that means that A times the coordinate of the first vector plus B times the coordinate of the second vector is equal to 0. So that's just the definition of the dot product. And I could be happy here noticing that I have an equation relating x and y that translates essentially through an equation what it means for x and y to be part of the line described above. Okay, usually we'll want to sometimes we'll keep it this way, sometimes we'll want to expand it, so I'll just expand it to show you something. So if I expand this, I get this. Okay. So I'm going to regroup the terms that include the variables x and y, and maybe I'll send on the other side the other terms. Okay, so that's a constant. I mean, in the sense that A and B, they're given to us initially. Okay, we're given the coordinates of the vector n. We're given the coordinates of a point on the line x0 or y0. So this is all fixed. Okay, so this is a constant. Okay, so what this shows us is that if I've got an equation of this form, where these are all constants, that's going to be the equation of a line. Okay, and that's going to be the equation of a line passing through some point, but mostly that's perpendicular to the vector AB. So the coefficients in front of x and y will give me for free the coordinates of a vector that's perpendicular to my line. Okay, so maybe let's summarize what I have found here. So the general equation of a line in R2 is of the form ax plus by equals to c, or there are different ways to write it down. Sometimes we can bring the c on the other side. So of course it makes it a minus c, but now change that minus c to c again, because it's a constant itself. So I could have this, essentially I could also have the constant brought to the left hand side, and that's still the equation of a line. Or we could also use this format here. So sometimes it will be written in this form. That's sort of called a point normal form for the line. Okay, so those are three ways to write down the equation of a line. Okay, maybe an example here. Okay, let's say example A. I'll look at maybe a line like this. Okay, so this is the equation of a line because it's of this form. Okay, what I get from my previous analysis are that the coefficients in front of x and y. Now, what's the coefficient of y? It's minus 1. So there's a little 1 hiding here, right? I could always write this equation in the form 2x plus minus 1y equals to 2. So the coefficients are 2 and negative 1. Okay, so this is a line perpendicular to the vector n with coordinates 2, negative 1, passing through, this is a little bit more difficult to obtain. Well, it's not that difficult, but we have to compute something here. So I need to find a point that belongs to that line. Now, this equation that I have, okay, it gives me all possible couples xy that define points that are part of the line. So if I assign a value to x, for example, let's say x equals to 1, okay? If I solve the equation for y, you will see that if you do that, you get 2 times 1 minus y equals to 2. So it's not too hard to see that. That means that y is going to be equal to 0. I get a point that's part of the line. For example, the point 1, 0. Okay? Usually what I recommend is actually being super lazy. You assign a value 0 to either x or y, and you solve for the other variable. If I assign a value of 0 to x, I'm going to get y equals to, I get minus y is 2, so y is negative 2. If you assign a value of 0 to y, you get that x is 1, which is the point I had originally here. See, x equals to 1, y equals to 0. But of course, you're not forced to do this. You can assign any value you want for x or y, and then you solve for the other variable, and you'll get a point. So that point, of course, is not unique. And by the way, the vector also is not unique. The vector n, if you can multiply that by any scalar, and let's say you multiply the whole vector by 4, you're going to get 8 minus 4. That's also a vector that's perpendicular to the line. So those this interpretation that you the interpretation that we wrote here, it's not unique in the sense that the vectors and the points that we chose are not unique. Maybe I can show you. Try to erase here. It's not working. Okay. Maybe the other form here. If I have 2x minus y plus 6 equals to 0. Okay, that's still a line perpendicular to what? Well, to, I look at the coefficients of x and y, 2 minus 1. But again, any scalar multiple of that would work. And then passing through, well, I just have to play the same game as before. Assign a value for x and solve for y. Like I said, be efficiently lazy, like I like to say it. So if I assign a value of y, a value of 0 to y, if I solve for x, I'm going to get x is minus 3. So I could choose the point minus 3, 0. Okay, and finally, the last form is the easiest in terms of the interpretation. Let's say I have this 3y minus plus 4, let's say, equals to 0. If I have it in this form, it's an equation of this form, so it's still the equation of a line. So again, what multiplies x and y are 2. Now it's 2 and 3. So those are the coefficients of x and y. If I multiply this out, right, I'm going to have a 2x and a 3y. So it's a line perpendicular to n equals 2, 3. And passing through, well, I could still assign my favorite value to x, but here we can be even more lazy in the sense that you see the x0 and the y0 are given in the equation. It's just that I have to write it in the form inside the bracket. It needs to be x minus something and y minus something. So the only thing I don't have is I have x minus 1, so it's going to pass through a point with coordinate x equals 1, and here I have to write it in the form y minus something, so that something is minus 4. And you can check, if you replace x by 1 and y by minus 4 in the equation, you're going to get 0 plus 0 for both. So both terms will be 0, so of course the equation is going to be satisfied. So so this form is a form that gives you automatically the coordinates of x of the normal vector n and a point. So that's why this last equation here for the line, that's called the point normal equation, because if you have a point and a normal vector, you can immediately write down the equation of the line. So I'll show you this here. So find the equation of the line passing through minus 4, 7 and perpendicular to 3 minus 5. So if I just want the equation of the line, I'm going to use the point normal form. That's the point normal form. Okay. So I just need to replace the right numbers. A and B are 3 and minus 5. And x0 is 4, minus 4 actually. So x minus x0 is x plus 4. And y minus y0 is this. And I have the equation of the line immediately. If I expand it, of course, I can write it in the form ax plus by equals to c, but I don't need to. If I'm just asked for an equation, I can give my favorite equation here. So here it would actually be minus 35 minus 47 if I'm not mistaken. Okay, but the point is that it's going to be of the form, this is of the form ax plus by equals to c. That's not a point normal form. It's just the expanded form of the point normal form. So this, try to be lazy here. Don't do a step you don't need to do. You can just stop here, and that's your point normal form, and this is your final answer. Okay.